Hi class, today we are starting chapter 5 and learning about exponential derivatives. So we're starting, today with a special exponential function, y equals e to the x. Okay, so e is actually a number, it's not a variable. So that's the first thing that is important for you to understand before we get going. Tomorrow next lesson, you're going to learn about the derivatives of other exponential functions, anything in general. But today we're just looking at e to the x because it has a special property in calculus, okay? So let's talk about what e actually is. So we all know exponential functions are used to model rapid change like population growth, bacteria growth, things like that. But in this section, we will study the exponential function y equals e to the x and its derivative. The number e is a special irrational number, kind of like pi. Okay, so pi is irrational because it has decimal places that go on forever. It has a special property. And e is called the natural number or Euler's number. So this looks like you would say Euler, but it's actually Euler. And it's after the Swiss mathematician Leonhard Euler, who lived in the 1700s. So e is actually the number 2.718. Well, that's the estimate to 3 decimal places. And it represents if you do 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, etc. on forever and ever. And in case you didn't know, factorial means multiplying all of the digits, the integers leading up to that. So for instance, 4 factorial would be, equal to 4 times 3 times 2 times 1. Okay, so another interesting fact is that 1 over 1 to the n, to the power n, approaches e, the number e, as n approaches infinity. Okay, so as we get closer and closer. So in calculus, though, e holds a very special property, which was discovered, and it has been very useful. So first of all, let's just kind of look at e to the x. So it's just an exponential function with the base of e, which I said is 2.718. So I'm going to be talking about the exponential and its log, which is its inverse. So I'm just going to be putting this line y equals x here. Okay, so since y equals e to the x is an exponential function, it has the same properties as other exponential functions. So it's just a bit steeper than, I don't know why that's different, 1 equals e to the x. Y equals 2 to the x. It's a bit steeper than that because e is slightly larger than 2. But think about it, it would still have an intercept here at 0, 1. And it would still grow. Okay, and it would still have an asymptote there. So this is 0, 1, because anything to the power 0 is 1. Even e to the 0 is 1. So this green function is y equals e to the x, and it is has a domain of any real number. Its range is greater than 0. It passes through 0, 1. Also, e to the ln x, I'll talk about ln in a second, is equal to x, and it has an horizontal asymptote at y equals 0. Okay, so now we should talk about the function log base e of x, which is the inverse of e to the x. Okay, it can be written as, this is called ln x. So when you see ln, that actually is just a log with a base of e. So it's called the natural logarithmic function, okay, because e is called the natural number. So it goes through 1, 0, and remember it's the inverse of the green function, so it should look reflected on the y equals x line. Okay, so it has a domain then that's greater than 0 and a range of any real number, right? Because they're inverses, domain and range switch. Passes through 1, 0. Ln of e to the x is equal to x, and it has a vertical asymptote at x equals 0. So the special property which we will explain more in depth in tomorrow's lesson why this is true. But the special property that e to the x has is it is its own derivative. So the derivative of e to the x is actually just e to the x. So the function is actually equal to its derivative. So if you want to find the derivative at any point, it's actually the same thing as finding the y value at that point. Okay, but what if you have a exponent other than just x? So in this case, we have e to the power of 3x. What is the derivative of that? So I can say the derivative of f at x, oh, sorry about this, with respect to the change in x. Oh, great. Of course, this is doing this during a video. Get out of here. Okay. So I'm going to take the derivative of e to the 3x times the derivative with respect to x times the derivative of the exponent, so 3x. Sorry, I made a mistake here. Sorry, guys. This is with respect to 3x. So treating 3x as the variable, and now this is with respect to x. Okay, so really you're just using the chain rule here. So this derivative is just e to the 3x, and this derivative is just 3. So you end up with 3 e to the 3x. Okay, I want to explain here why these two things are equal. Okay, so what does this mean here? This means that the derivative of e to the 3x with respect to 3x. So it's treating 3x as the variable. So think about it as blah. So we know that e to the blah has a derivative of e to the blah. So when you just are looking at blah as a thing, okay, as just one package. So e to the 3x, its derivative is e to the 3x if you're thinking about just 3x as the variable, but then we have to multiply it by the derivative of what that exponent is. So if you have the number e raised to some kind of function, anything other than just x, then its derivative is the same. So you keep e to the g at x the same, but then you got to multiply it by g prime. Okay, so it's the whole power times the derivative of the exponent. So let's do some examples here. Okay, so first we have just e to the x squared minus x. So again, it's just you leave it the same, e to the x squared minus x, and then you multiply it by the derivative of the exponent, so 2x minus 1. Okay, and then that's it. You can leave it like that. So this one is first and foremost a product rule, okay? You can see x squared and e to the x and think about them as two separate functions. So we can take the derivative of the first one, 2x, and then leave the second one the same. And then add, now you leave the first one the same, and multiply it by the derivative of the second one, which is still just e to the x, because e to the x has a derivative of e to the x. So now what you can do, notice, is you can actually factor out an x and an e to the x, and you're just left with 2 plus x in the brackets. All right. Just want to make sure I did that right. Yeah. All right. So that makes it nice and easy to common factor. Okay. These two here, sorry, they should say f at x equals before them. Okay, so these are a little bit more complicated. So again, it's helpful to think first and foremost, is this a product rule? Is this a quotient rule, a chain rule? What is it? Well, this is first and foremost a product rule question. Okay, I have this function multiplied by this function. Okay, so when I take the derivative, I'm going to think about it as a product. So I'm going to leave the first one the same and then multiply it by the derivative of the second one, which is just e to the x. And then now I'm going to take the derivative of this first one, which is chain rule. So I take down the 2, I leave the 2x minus 1, and then I multiply it by the 2, and then e to the x. So notice here, I can actually factor out an e to the x and a 2x minus 1. And then I'm just left with a 2x minus 1 plus 4. Okay, because this 2 and times this 2 is 4. So this factors pretty nicely down to e to the x, 2x minus 1, 2x plus 3. Pretty nice and neat. Okay, this is first and foremost a quotient rule problem. So I'm going to change the color just so we can keep this clear because it's a bit long. I should have maybe left more space for it. Okay, so let's think about this really clearly. So we have the bottom, kind of write this small, times the derivative of the top. So the derivative of e to the x is just e to the x. Okay, and then I have minus the derivative of this. So I'm going to bring down this minus 1. So the two negatives are going to cross off to become a positive, and it's just going to be e to the negative x. Okay, so I brought down the negative 1 with the minus, it becomes positive, and then that stays the same. Okay, so that's the bottom times the derivative of the top minus the top. That's a negative, times the derivative of the bottom. Oh, I was really hoping to put this in here. Guess we'll just do it below. So the derivative of the bottom is e to the x plus a negative. So that's going to be minus e to the negative x. Okay? And then this is all over the bottom squared. So this is going to actually do a lot of cool crossing out. Okay? So remember our exponent laws. When you're multiplying powers with the same base, you add the exponent. So e to the x times e to the x is e to the 2x. And then e to the x times e to the negative x is e to the 0. Okay, and then same thing here. You get another e to the 0. And then you get e to the negative 2x. Okay, and then you subtract e to the 2x. What was I going to do here? Minus, where is this? E to the 0. Yep. So minus e to the 0, minus e to the 0, plus e to the negative 2x. Okay, and that's all over the denominator. So now watch what happens. E to the, oh, that should have been a 2 here. Okay, so e to the 2x minus e to the 2x goes away. Now e to the 0 is actually 1. So I get 1 plus 1, and then e to this minus 2x minus e to this minus 2x, those go away too. And then the negative negatives become positive. So plus 1 all over the denominator. So we actually get 4 over the denominator, e to the x plus e to the negative x, all squared. And that's your derivative. Okay. All right, let's do this next example. 3 times e to the x squared. We want to determine f prime at 1. So first, let's determine f prime. So we can think about this as, a product rule if you want. So the derivative of the first thing is 0, so that goes away. Then we add it to, we keep 3 there. And then e to the x squared, when it's taken its derivative, we leave e to the x squared, and then we multiply it by 2x. So this derivative is actually just 6x times e to the x squared. Okay, so if we have f prime at -1, we have -6 times e to the 1. So we can just leave this as -6e. Okay, so I would just leave it like that because that's an exact number. Just like if we had pi, we would leave it as pi instead of estimating it since it's not within a word problem. Okay, determine the equation of the tangent where x equals 2. So the equation of the tangent line will have a slope of the derivative. So let's remember that. And then we can figure out this other stuff later. So the slope of this line is equal to dy dx. Okay, so this is first and foremost a quotient rule problem. Okay, so we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we can take out an x and an e to the x, and we're left with x minus 2 over x to the power 4. So we can cross off one of the x's, so e to the x times x minus 2 all over x cubed. All right, so now if we let x equals 2, then dy dx is equal to e squared, 2 minus 2 over 2 to the power 3. So this is just actually equal to 0. So therefore, this tangent is actually a horizontal line, which is no problem. It just means that the slope is 0. So therefore, we need to find out what is y at 2. So when x equals 2, y is equal to e squared divided by 4. So we're actually just going to leave that because it's an exact number. So this is the equation of the line because it's a horizontal tangent. Okay. Last example, a word problem. So the number of rabbits in a forest at time t is represented by this function, which has an e in it. What is the initial number of rabbits in the forest? So that would be at time is 0. So be careful here. This doesn't mean that this is 0. So we would have 500 times 10 plus e to the negative 0 over 10. So be careful. E to the 0 is actually 1. So this is actually 500 times 11, not times 10. That doesn't go away. So you get 5,500 rabbits as the initial number. Okay, and then it asks us for the rate of change. So that is just the derivative. So you would have 500 times the derivative of what's inside here. So the derivative of 10 goes to 0. And then e to the negative 10, t over 10. The derivative of the exponent is minus 1 over 10. And then we leave the e to the negative t over 10 the same. So this multiplies to negative 50 e to the negative t over 10 as the derivative of that function. And it just asks for the rate of change at time t at the general time. So that is the answer. All right, so check out your success criteria, take a look over the examples, and hopefully you learned a lot about finding the derivative of e to the x. All right, thanks for watching, guys. Hope you learned lots.